This is applied physics course, and we are going to discuss today chapter 8, part 1, the rotational kinematics. I am Dr. Nasir Mirza, and this is applied physics course for undergraduates. As we know very well that rigid bodies are what we are considering in the mechanics, and the analysis model introduced so far for the rigid bodies cannot be used to analyze all the types of motions. Rotation is one of those which cannot be explained through linear motions. So we can model the motion of the extended objects by modeling them using system of many particles and by considering the center of mass. We have seen that the center of mass concept simplifies and creates an easy way to solve the mechanics of uh, linear motions for such objects having extended distributions. The analysis of rotation is another uh, important thing that we have to consider for the simplification if the objects are to be assumed as rigid bodies. Rigid bodies are those bodies which cannot be deformed. Most of the bodies have some flexibility that they can be compressed or elongated or extended. However, true rigid body is an ideal concept and it is really not deformable. Relative locations of all particles that make up the object for a rigid body remain constant. All the real objects are not rigid bodies. They are deformable to some extent, but the rigid objects model makes the mechanics very simple and very useful in many situations where the deformation is negligible or relatively small. So to understand the rotation, we first introduce the concept of the angle and the angular position and the angular change. The axis of rotation is the center of uh, our rotating object. For example, here we have a disk. So to define the angular position for the disk, we have to have a fixed reference line, and we choose this x-axis as the line. Or we can choose any other reference, for example, y-axis, for example, any other line. Here we choose a fixed reference line, and then point B is at a fixed distance r from the origin, you can see, and a small element of the disk then can be modeled using as this P point. The polar coordinates are the convenient uh, coordinates to be used for the position representation. A particle now is located at r distance from the origin, and it is making an angle theta with the x-axis, and the angle theta is measured counterclockwise in this counterclockwise manner. The counterclockwise is the rotation against the motion of the hands of the clock. So from reference line X, we move up towards Y, and this is the counterclockwise. Now we have to have some definition of the angle. So if there is a rigid body, for example, this is a rigid object, and it has a point P, and P point moves through this arc length S, and we are showing here a rotational circle, and the arc length is not the straight line distance, and arc length S is this tilted or kinked distance. The arc length and the radius is the distance from the center to the point P. So on this two-dimensional picture, x prime and y prime coordinates, this S and R are shown with respect to point P. The angle phi is the phi angle which is made in the counterclockwise direction as we move up. Then the angle definition is that it is a ratio of the arc length to the radius. So S divided by R is the angle. Since both are the lengths, therefore the angle is basically without any dimensions. The angle defined in this way are always given in the units of radians. The angle is the ratio of two lengths, and it is a pure number. It has no dimensions. It does, however, have units, and units are radians in this case. Because total circle circumference of a circle with a radius r is equal to 2 pi r. Therefore, the total angle developed in a circle is the total arc length divided by the radius, and it is 2 pi r divided by r. It means the particle moves in an arc length of one circumference, then it must trace out an angle 2 pi. 1 radian is the angle subtended by the arc length equal to that of the radius of the arc. When we use the rotation equation, we must use the angles that are expressed in the radians. One complete revolution is equal to 360 degrees. People have distributed the total circle into 360 small angles. Then this 360 degrees term is equal to 2 pi radians. Then 1 radian is 360 degrees divided by 2 pi, and it is equal to 57.3 degrees. Now we consider the angular displacement and the angular velocity. The idea is similar to that of the linear displacement and the linear velocity. Let us consider a body as shown in the figure, which is rotating in the counterclockwise. At time t1, it is at the position P. From A to P is the length, and the angle subtended is phi 1. So at time t1, the angle is phi 1. Later, it goes to the point, another point, which is a new AP, and it is at time t2, then the angle, new angle is phi 2. So the figure shows that the position of the point P is changing with the time, and with respect to the reference line, its angle is also getting displaced. So the total angular displacement from time t1 to time t2 is given by phi 2 minus phi 1, and the time interval is t2 minus t1. We define the average angular velocity as omega, average of the particle P in this time interval, equal to omega average, which is equal to phi 2 minus phi 1 divided by t2 minus t1. And you can see that this is delta phi divided by delta t, which is the angle, uh, change in the angle divided by the change in the time. So this is the average angular velocity, or which is the rate of change of the angular displacement. Now we consider the instantaneous angular velocity. It is the velocity of the particle in the limit, when the limit approaches to uh, such a point that the delta t, t2 minus t1 goes to 0. In that limit, the delta phi over delta t is defined as a new instantaneous average or instantaneous angular velocity, and it is actually said to be the first derivative, because in calculus such a limit has a name of d phi over dt. This is the derivative, uh, first derivative of the phi, the angle with respect to time. So if angle depends on time, the displacement depends on time, its derivative is the instantaneous angular velocity. Then angular acceleration is defined as the average angular acceleration given by change in the angular velocity omega 2 minus omega 1 within the time t2 minus t1, which is equal to delta omega divided by delta t, and this is the average acceleration. Instantaneous angular acceleration is the limit of above ratio when the time interval delta t equal to t2 minus t1 approaches 0. When this limit is taken and the answer is calculated for the limit, we get the first derivative. It is the first derivative of omega, the angular velocity. Now we know that the instantaneous angular velocity is the first derivative of the angular displacement. Therefore, the angular acceleration, the instantaneous angular acceleration, is the second derivative of the angular displacement. Remember, the dimensions of the angular acceleration are inverse of time squared. Units are radians per second square or revolutions per second square. The angular velocity can be positive, it can be negative, according to whether the angle is increasing or decreasing. Its dimension is the time inverse, 1 over time. Units can be the radians per second or revolutions per second. So whenever we are going to use angular velocity, it means instantaneous angular velocity. Whenever we are going to say the angular acceleration, we mean instantaneous angular acceleration. Let us do this simple example. A child's top is spun with angular acceleration alpha equal to 5t square, 5t cube minus 4t with the t in seconds and a in radians per second square. It is the angular acceleration alpha. At time t is equal to 0, the top has angular velocity 5 radians per second, and the reference line on it is at angular position theta equal to 2 radians. Question asked is obtain an expression for the angular velocity of the top as a function of time. So we use the definition of the angular acceleration as rate of change of angular velocity. So d omega over dt is the angular acceleration. Therefore, d omega is equal to angular acceleration multiplied by dt. we substitute the angular acceleration value as 5t cubed minus 4t and then take the integration. When we take the integration, we receive the answer as we have to integrate the t cube, and the whenever there is a power of the variable uh, for which we are doing the integration, the power increases by 1 and the value is also divided. So here 3 is increased by 4 and divided by 4, and the answer is 5 divided by 4 into t to the power 4. In the next part, minus 2 uh, appears because this was 4 multiplied by t to the power now 2 divided by 2, and when we divide by 2 we get the answer as 2 plus a constant of integration. To find the constant of integration, see, we note that this given angular velocity at initial time is 5 radians per second. So we substitute the t equal to 0 and omega equal to 5. We get the answer c equal to 5. Therefore, the complete answer is omega equal to 5 by 4 t to the power 4 minus 2 times t square plus 5. Let us do another example. In this example, a fan blade is initially rotating at an angular speed of 48.6 RPM. RPM means revolutions per minute. It slows down and comes to rest in 32 seconds. After turning through a total of 8.8 revolutions, find the average angular velocity and average angular acceleration. So we have to find the average values. We know very well that the average angular velocity is delta phi over delta t, the total angular displacement divided by the time interval. And we are given here the 48.6 revolutions per minute. And the time total is also given to us in 32 seconds. The turning of total 8.8 revolutions, we are asked to find this. So 8.8 revolutions are the total number of revolutions divided by the total time 32 seconds. We get the average value as 0.28 revolutions per second. The W1 is given to us 48.6 revolutions per minute. We convert it into the revolutions per second. Then we find the what will be the other velocity, and we can find out the other velocity as well, because delta omega divided by delta t is the average acceleration. Since at time t is equal to 0, the blade was doing this. Now it has come to rest in the 32 seconds. Therefore, its final value is 0. So 0 minus 0.81 revolutions divided by 32 is the answer for the average angular acceleration. This negative sign means that the fan was deaccelerated. Now we come to important idea that rotational quantities are vectors or not. Roughly speaking, we can say that the position, velocity, acceleration of a single particle are all vectors. If particle is confined to a straight line, we do not really need vector notations, but we know that it is vector. Such particles that have two directions available to it, they indicate their direction plus minus signs, and we can find out where they are, and we can specify them as vectors. In same way, the rigid bodies that are rotating about a fixed axis can rotate clockwise or counterclockwise along some axis. And again, we can select the directions by means of plus and minus signs. So we can treat the angular displacement, the angular velocity, the angular acceleration of the rotating bodies as vectors. Yes, we can. We can qualify. And also with some reservation. We have to look into this. A record is rotating about a vertical axis that is coinciding with the axis of its spindle. The angular velocity of the rotating record can be represented by a vector lying along the axis, pointing downward, as we are showing. The angle of the rotation and the angle of the hands, fingers, and then thumb is pointing towards the direction. So we can establish the direction of the angular velocity vector downward by using the right hand rule. And fingers will always be telling the right hand curl around the record and pointing the way it is moving, and then the extended thumb will be pointing in the direction of the velocity. This right hand rule, as shown in the previous figure, is really when you curl your right hand about the rotating record, your fingers are pointing in the direction of rotation, and your extended thumb will then point in the direction of angular velocity. The large angular displacements cannot be treated as vectors. However, we represent them as vector quantities because we think and consider the rotations to be small. If some quantity has to be a vector, then vectors additions rules must be obeyed. We say we can add two vectors in any manner. For example, a vector is added to a b vector, and we say we can add a b vector to a vector, and then same answer will be the resultant answer. A plus b vectors will result in some final form, then b plus a vector will have the same form. However, we have seen that if the angular displacements are large, the angular displacements fail this test. Let's see how. Large angle rotations, let us see. Here we are showing in the first figure that we are rotating through an angle of 90 degrees this book. As we rotate, the top of the book goes to this direction. And we have given a 90-degree rotation. After this, now we rotate about z-axis. When we do this z-axis rotation, the book is now facing in the other direction, and this is the surface and its position. So now this is the final shape as we have rotated from the first rotation and then the second rotation. We perform the second rotation first. In the beginning, if we are going to rotate through the z-axis, this book will get rotated in this form. Once it has been rotated, then we rotate it by with the help of x-axis, and we see that the book is now lying on this surface, and its position and the shape is entirely different as compared to the first. So it does not match. So the theta 1 plus theta 2 is not equal to theta 2 plus theta 1. The large angle rotations do not obey the commutative law. So if we treat them as vectors, this is shear violation that has happened. However, if the angles are very small, less than 20 degrees, then we see that the commutative law is not violated. It is really obeying. Here we have the 20-degree rotation about x-axis, and then 20-degree rotation about z-axis, and the final form is this. Similarly, the book has the 20-degree rotation about z-axis, and then 20-degree rotation about the x-axis, and it has the similar. So the conservation of this law a plus b equal to b plus a vectors commutation addition is observed if the angle is small. And we are going to treat the rotations for the small angles, and therefore we will treat them as vectors. So rotational quantities have this tendency that if the angular rotations are represented by vectors, then the displacements must be very small. And if this is the case, the angular velocities can always be represented as vectors. Now, rotational quantities, if they are treated like vectors, then the right-hand rule will define the direction of the vectors. The displacement vector d theta, the angular displacement d theta, and the angular velocity omega, and the angular acceleration will be having consistent vector formulation. And all will be treated as vector quantities. Only the time is scalar. If the rotations are considered, then let us consider a simple example of constant angular acceleration. Consider z component of the angular acceleration as a constant, and alpha z is constant. Then d omega z over dt is constant. Then d omega is equal to alpha times the dt with the z component. And now we put the integration, that is, we are going to integrate this equation with respect to time on both sides. The d omega is integrated and the alpha times dt is integrated. The alpha is constant, therefore it can be taken out, and the dt integration will lead us to time t plus a, the constant of integration. And d omega integration will lead us to only omega, the z component. When t is equal to 0, the omega z is equal to omega naught z, the initial value. Therefore, our constant of integration a will be omega naught z. And therefore, the final form of the equation will be omega z equal to alpha times t plus omega naught times z. This is very similar to the kinematic equation that we have already seen for the linear motion, where velocity vz is equal to the acceleration az times t plus v naught z. Here we have the final form omega z equal to alpha z times t plus omega naught z. Here alpha is the angular acceleration, omega is the angular velocity. So all the angular quantities are showing the similar kinematic equation. We can use this equation further and use the definition of the omega, the angular velocity, as d phi over dt. Once we multiply by the dt, and d phi is then equal to omega z times dt. The integration with respect to time will give us d phi integral equal to the integral of alpha t plus omega naught z times dt. We now have to integrate this t, and here there is no t, therefore a constant, and we will get the time variable. So the answer is for the first integration, the phi, and for this integration, half alpha z times t square, because t uh, has increased by power 1, and the value of this power is also written here as a uh, denominator. Similarly, for omega naught z multiplied by 1 has been converted into t because of the integration, and the constant of integration appears. If the angle was originally phi naught at time t is equal to 0, then a becomes phi naught, and the final form of the equation is this. The final form I read is half alpha t square plus omega t plus phi. All are for the z. This expression of the angular displacement is very similar to what we have already seen for the linear displacement, where we have used the x coordinates, or the s equal to half a t square plus velocity, initial velocity times t, plus the initial displacement value as x naught, or the s naught. So if I consider the rotation with the constant acceleration, I come to know that the translational motion with the constant linear acceleration has shown me the series of equations. Those equations were termed as kinematic equations. Now, linear equations are V naught plus AT equal to V, S is equal to V naught times T plus half AT square, V square is equal to V naught square plus 2AS, the displacement S equal to 1 over 2 times V naught plus V times T. Similarly, the angular equations are omega is equal to omega naught plus alpha T, theta is equal to omega naught times T plus alpha T square by 2, and omega square is equal to omega square naught plus 2 times alpha times theta. So wherever there was a displacement, now it has become angular displacement. Wherever there was velocity, it has become now angular velocity. Wherever there was acceleration, a, it is now the angular acceleration. So similarity is tremendous, and we can have the equivalent quantities in the angular kinematics. We will use these kinematic equations for rotational motions, as we have been using the linear kinematic equations for the translational motions. Let's do one simple example on this. Starting from rest, a grindstone rotates at a constant angular acceleration, alpha equal to 3.2 radians per second square, and when time is equal to 0, it has a reference line AB on a horizontal plane at an angle position theta equal to 0, and find the angular displacement reference line and the angular speed after 2.7 seconds. Since the initial angular displacement is 0, initial angular velocity is 0, and initial acceleration is given 3.2, we can use the accelerations equation, kinematic equation. Phi, the angular displacement, is equal to half alpha t square plus omega 0 times t plus phi naught. Now these values are 0, and substituting we get the angle phi as 11.7 radians. Then the angular speed can be calculated as alpha times t plus omega naught. Omega naught is 0 and alpha is given, t is given, then angular velocity is calculated. So both quantities are very nicely, very simply calculated if we know what kind of kinematic equation we have to use to reach at the answers. Are there any relationships between the linear and the angular variables? Yes, there are. We will see. When a rigid body, such as a merry-go-round, rotates around an axis, each particle in the body moves in its own circular orbit, and the object or the body is rigid. So all particles make one revolution in the same amount of time. So they have the same angular speed. However, the farther the particles from the axis, the greater is the circumference of the circle. So the faster they are with their linear speed. So we notice that on a merry-go-round, you turn the same angular speed omega regardless of your distance from the center. But your linear speed increases noticeably if you are moving outside the edge of the merry-go-round. So there must be a relationship between the linear velocity and the angular velocity. We will discuss this in our next lecture on the kinematics of rotation. And until then, we have to wait and see how these things can be related and how we can figure out the acceleration, the details of the accelerations of the rotating objects. Thank you so much. We stop here.